Okay, so we're going to look at circles touching then. So obviously, if a circle is going to touch, and we're looking more here at touching rather than intersecting, which was, I suppose, a separate video. So we're looking just at touching at one point, and that can happen either internally or externally. And when we're talking about this kind of, I suppose, the two circles touching, we're going to be looking at the distance between their centers and how that corresponds or lines up with the radius of the two circles then. So if we start with externally, because that's probably the most obvious one to see, if two circles are touching externally at one point here, then the distance between the two centers is going to be equal to the sum of the radii. So the distance between the two centers should be the same as if I just added the two radius. Then internally, then the distance between the two centers will be the bigger of the two radii minus the smaller of the two. Okay, so the distance radius 1 minus radius 2. Okay, the note I suppose that I've put here as well is one that's worth kind of reminding yourselves of. If a circle is touching, okay, if two circles are touching, then that point of contact and the two centers of the circle are going to be collinear. They're all going to be in a straight line with each other, and that line, kind of that distance that we're looking at here, or between the two radii. So a point that's worth noting here because it can be quite important for us when we're looking at other questions. So looking then straight into the examples here, show that the circles touch externally. So what we know, I suppose, here is if they touch externally, we're expecting then that the distance between the two centers is going to be the sum of the two radii. So we need to find my two centers here. So let's go with my two circles. So for circle 1, the center is going to be, well, let me see, we know 2g is minus 2, so g is minus 1, so the center is 1, 2. And then the radius is the square root of minus 1 squared plus minus 2 squared minus minus 4, which is 1 plus 4 plus 4, which is 9. So the radius is 3. For my other circle then, the center is going to be 4, 6. And my radius then minus 4 squared plus 6 squared minus 48. So we get 16 plus 36 minus 48. And again, we can kind of see where that's going to simplify down for us. 4, so radius is 2. Looking at the distance between the two centers then. So that's x2 minus x1 squared plus y2 minus y1 squared. So we get 3 squared plus 4 squared, which is 9 plus 16, which is root 25, which is 5. So looking at my distance then, I want the distance to be equal to the sum of the two radii, and is 5 equal to 3 plus 2? It is indeed. Okay, so therefore they touch externally. Okay, and as simple as that really is all that we really need to show. They touch externally because the distance between the two centers is equal to the sum of the radii there. Next thing we want to do now is show that these two circles touch internally. So internally, I'm expecting the distance to be one radius minus the other one, where obviously the distance must be positive, so I must take the smaller radius from the bigger radius. So going again the same as before, C1 here is going to be center minus 2, 3, and on the other circle, my center is going to be 0, 3 over 2. Okay, so a slightly different one for us here, not just as clean cut. The radius of my first circle here then, 2 squared plus minus 3 squared plus 12 is 4 plus 9 plus 12, which is 25, which is 5. The radius of the other circle then, 0 plus 3 over 2 squared plus 4, so 9 over 4 plus 4, which is going to give me 25 over 4, which will break down to 5 over 2 when I do my square root there. So looking now at the distance between my two centers, okay, so I'm doing minus 2 minus 0 squared, 3 minus 3 over 2 squared, so that's minus 2 squared plus, let's see what 3 minus 3 over 2 gives me. Gives me 3 over 2. Okay, so we get a distance of 4 plus 9 over 4, which is going to be 25 over 4, which is 5 over 2. Okay, so we're checking now, is this distance the same as radius 1 minus radius 2? Is 5 over 2 the same as 5 minus 5 over 2? And essentially then, is 5 over 2 equal to 5 over 2? And of course it is. So jumping into some of these exam questions here, now what we're going to see with some of these questions is that there's in some cases two ways to kind of look at them, particularly questions where we want to find points of contact. So one way we can kind of look at it is in terms of divisor of line segment. And if you remember when we looked at divisor of a line segment, we did also note that we could look at them as translations as well. So we're going to see that coming up a little bit here in some of these questions then. So looking at the first question, we need to show that these two circles touch externally. So same as before, that means that the distance must be equal to the sum of the two radii. This one really following the exact same approach as we've had already. So minus 2, 1, the centre of the first circle here, the centre of the second circle is 7, 13. The radius of my second circle is root 25, so 5. The radius of my first circle here then being 2 squared plus minus 1 squared plus 95. So 4 plus 1 plus 95. So that's root 100, which is just 10. And getting the distance between my two centres then is going to be, see, start with x, 7 plus 2, so minus minus 2, and 13 minus 1 squared is 9 squared plus 12 squared. So 81 plus 144, which is 225. And square root of 225, I believe, is 15. Yeah, 15. So checking then, is the distance the same as the sum of the two radii? Is 15 the same as 10 plus 5? And of course it is. Therefore, they touch externally. And always good to just round it off by really nearly restating the question, or what were you asked to show, and stating that you have shown that you recognise that that's what you've shown. Looking at the next exam question then, so this is 2013. So the circles touch externally as shown. Complete the following table. We're given very little information here, but we're given centre and we're given radius for the first circle. So once I'm given centre and radius, I tend to go for the format, or for this equation of the circle here. It's just the easier of the two, and that's the information that I have. To find then the other information from my circle here, well, looking at the equation, I know that my centre is going to be 1, 1. The radius then is 1 squared plus 1 squared plus 7, which is going to be root 9, which is 3. So the radius is 3. So marking some of these things in, I have a radius of 2, radius of 3, circle 1, so this is minus 3 minus 2, this is 1, 1. Okay, and this is where I'm saying, I suppose, that we can find in these sort of questions that sometimes what we're looking for here could be solved by translation, could be solved by ratio, could be solved as divisor of a line segment, because what we can see is that my point here, if I call it P, the point of intersection, splits those two centres in a ratio of 2:3. So if we consider that kind of overall movement, I would be going maybe 2/5 of the way as opposed to 3/5 of the way then to get to the other centre. So that's what we're going to be looking at a little bit now in the part B here. So find the coordinates of the point of contact of C1 and C2. Okay, so we kind of have two ways we can look at that. We can either use, I suppose, nearly a simultaneous equation for my two centres, find the equation of the common chord, and then find the point of intersection for the two circles. And if you want to approach that one, I suppose really going back and watching that video for intersection of two circles would be the best place to go for that one, and then kind of from there kind of apply that to this question. Just for the sake of the video here, just to show an alternative way, I'm going to focus maybe more on finding those coordinates first, and then seeing can we find the equation of the tangent, just to approach it in a slightly different way. So the two ways that I'm looking here at finding that point of intersection are either to do it by translation, or to do it by looking at a divisor of a line segment. So if we were to look at it in terms of a divisor here, what I'm saying is that if I have my centre 1 here and my centre 2 here with my point of intersection in the middle here, this point of intersection splits those 2 points, or that line segment, in a ratio of 2:3. And we have a lovely formula for using the divisor of a line segment. Okay, so that's from our kind of our equation of the line section there. So if I was to use that formula, it would be 3 by minus 3 plus 2 by 1 over 3 plus 2, and 3 by minus 2 plus 2 by 1 over 3 plus 2. And we're just trying to find what is the point that splits these two, or this line segment, in this ratio. Minus 6 plus 2 over 5, and I'm getting an overall result minus 7 over 5 and minus 4 over 5. Okay, as my overall point P there that splits those. So that's my point of contact there. And again, it's using that idea that we had already where I said that the centers in that point of contact will be on the one line, on that one line segment. If we want to consider it nearly as more of just a translation, my first center here is minus 3, minus 2. I'm moving to a point P that I don't know, and then I'm moving to the second center then, or the center of the second circle, which is the point 1, 1. So looking at this movement overall, in terms of just moving from one point to the other, that's a movement of plus 4 on the x coordinate and plus 3 on the y coordinate. Now we know that this movement is a 2:3 ratio, and what that means for me here is that this movement from C to P is 2/5 of the overall movement. Whereas then once I get to P and I want to go to the next center, I move the other 3/5 of my movement. So since we know that we've moved 4 in the x coordinate, for example, I know that I only need to go 2/5 of that way to get to point P. So looking at the x coordinate just first of all, I'm going to see, well, what is 2/5 of the way there? And 2/5 of the way would be a movement of 8 over 5. Same with the y coordinate. I know I've got a movement of plus 3, but if I only go 2/5 of the way, that's a movement of 6 over 5. So taking my point minus 3, minus 2, and just moving that much, so 8 over 5 and 6 over 5. So instead of moving the plus 4 and plus 3, I'm just doing 2/5 of that movement to see where that takes me. So let's have a look. Minus 3 plus 8 over 5 is going to take me to minus 7 over 5, and minus 2 plus 6 over 5 is going to take me to minus 4 over 5. So as we found out already, we end up at the same point. So either translation or divisor of a line segment, both giving me the exact same results there. So both leading me to really the same point. We're asked now, hence or otherwise find the equation of the tangent. So I'm going to approach this, I suppose, as if this is what I had done first. So I've found my point of contact. I want to find the equation of the tangent. So the one thing I'm going to make note of is that the tangent is perpendicular to the line from the radius, or the line from the center, excuse me. And we could even say it's perpendicular to the line segment AB. Okay, so it's going to be perpendicular to my line segment AB there as well. So I could use that to look at this point that I'm going to be doing here. So whatever line segment I'm looking for has to split my line in that ratio, and it has to be perpendicular to that line segment then. So finding the slope of AB first of all. So I suppose it's not AB here, it's really C1, C2 is what I've been calling it. So let's go with that. So finding the midpoint, or the slope of that, excuse me, 1 minus 2 is 1 over 2, and then 1 plus 3. So I'm getting a slope of 3 over 4, which means the perpendicular slope is going to be minus 4 over 3. So I want the equation of the line that has a slope of minus 4 over 3, and that passes through that point, minus 7 over 5, minus 4 over 5. So filling all those points in, y plus 4 over 5 equals minus 4 over 3, x plus 7 over 5. So y plus 4 over 5 minus 4 over 3x minus 28 over 15. I'm going to multiply across, I suppose, by 15 here to kind of tidy up a little bit. So 12 minus 20x minus 28, and I get 20x plus 15y plus 40. And if I can divide across here, I suppose, by 5 to get 4x plus 3y plus 8 equals 0. And as we said here already, you could easily find your point of intersection, or your common chord for those two circles. This would be your common chord. Find that first and then find the points of intersection, just to show a different way. And I suppose to show you that given the way they've laid out the question there, it was possible to do it in that order, because we might automatically think I'll find the tangent first. They did give you the option, they gave you the otherwise, so you were free to, I suppose, do it that way as well. You weren't, I suppose, just restricted to following that exact version, but just to give you, I suppose, a different look at the sort of questions that we can have here, or the sort of approach we can take. So looking at, I think this is our last exam question here, or our second last exam question. Prove that the circles touch internally. So to prove that these two circles touch internally, we need to show that the distance between the centers is one radius minus the other. So again, I'm finding my two centers first. So that's going to be 2, 3, and 3, 4. Getting the radius then, minus 2 squared minus 3 squared minus 5 is 4 plus 9 minus 5, which is going to be root 8. Okay, the radius on the other side here, 3 squared, 4 squared minus 23, which is going to be 9 plus 16 minus 23, which is root 2. Okay, so 25, so root 2 there. Now root 8 can be broken down to 2 root 2. The distance between the two centers then, next thing we have to find. So let's do 3 minus 2 squared plus 4 minus 3 squared. And that's just going to simplify down to 1 squared plus 1 squared, which is root 2. So we need to show now, is the distance equal to the bigger radius minus the smaller radius? So is root 2 the same as 2 root 2 minus root 2? And of course we can nearly see straight away that it is indeed. Okay, so then they touch internally as required. Okay, looking at the next part of the question, then we're asked to find the coordinate of the point of contact of the two circles. So as we had before, we can either do this by doing simultaneous equation, find the equation of the common chord, and then use that then in finding the exact point of intersection, or we can look at it with a translation. Again, I think for this case, I'm just going to show you the translation version. If you want to do out the point of intersection for yourself, you'll be able to check then and make sure that you've got the right answer. I can give you the equation of the common chord here as well. But just to look at it with a translation idea, just to show us something different here, I'm going to just kind of give an example of my two circles here. Let me just put on the ink to shape. So this, I suppose, is potentially what our two circles might look like. Now, again, it's only a sketch really for visualization purposes. But looking at the two circles that I have here, so if I have one circle here and another circle here, one of the centers being 2, 3, the other being 3, 4. Okay, it doesn't really matter. Obviously, they wouldn't be exactly in line like this. It's more likely that one would be shifted up a little bit, but just again to be able to see here. We know from our work already up here that the distance between my two radii here, so the radius of the bigger circle, that's going to be this full radius that I'm marking in red here. This full radius is 2 root 2. Okay, the radius of the smaller circle marked in blue here is just root 2, and that's going to extend to the other side here as well, being root 2. So what we can actually see is that this point here in the center is actually splitting those two circles, those endpoints, in half. This point on the edge here, which we'll call P, is the point of intersection. That's where the two circles are touching. Okay, so really what's happening here is that my circle 2, the center of that circle is actually directly the midpoint of 2, 3, and the point of intersection there. Okay, so if I think about this in terms of translation, okay, I have my center 1, I have my center 2, and I have my point of intersection here. So I have my point 2, 3, my point 3, 4, and I have my point of intersection that I don't know. The distance from here to here, the movement that I'm doing, is +1 in the x coordinate, +1 in the y coordinate. And the ratio I'm looking at is that distance there is actually a distance of root 2, as is the distance from center 2 to my point of intersection. So what we actually have here is an exact 1:1 ratio. So if I want to make that movement then from the center to this next point, I'm literally just going to be doing another +1 +1, which will take me to 4, 5 as my point of intersection there. Okay, so exactly in the middle of that point there. Another way we could think about it is to do kind of that, to do the divisor of a line segment, even particularly divisor of a line segment here when it's a midpoint, we can literally just use midpoint formula. So you're looking at something like 2 plus x over 2 and 3 plus x over 2, knowing that the answer here is 3, 4, because that is the midpoint. We'd then be saying that 2 plus x over 2 equals 3, So 2 plus x equals 6, which means x equals 4. And similarly, 3 plus x over 2 equals 4. 3 plus x equals 8. X equals 5, or y equals 5, excuse me. It should be y there, of course. Okay, so another way to look at it, finding the midpoint and recognizing that that is the midpoint. A lot of this really not visually clear until we've kind of laid it out. And even without the diagram there, if we just had the right hand side where we've labeled the centers and filled in the different lengths there, that would kind of make it that bit clearer for us, and that little bit clearer. If you want to approach it looking at common chord and looking at point of intersection and all of that, the equation of your common chord, just to make sure that you're working on the right track, the equation of your common chord that you should get is x plus y minus 9 equals 0. So that will be your common chord there, and then you find those points of intersection. You should end up then with the same points of intersection that we have here, which is the point 4, 5. Okay, so again, just trying to show different ways here of approaching these questions. So we've one last exam question to do, the 2015 question. So two circles touch internally at B as shown. Okay, we don't have a diagram, but we can imagine. So the equation of S is given, write down the center and radius. So the center here is going to be, so we're making sure we remember that it's x minus k, or x minus h, y minus k. So the center is 1 minus 6. The radius squared is 360. So the radius is the square root of 360. So let's just see what that gives me. Root 360 gives me 6 root 10. Okay, not the nicest radius we've had, but it works. The point K, okay, here's our diagram here. The point K is the center of circle C. The radius of C is 1/3 the radius of S. The coordinates of B are 7, 12. Find the coordinates of K. Okay, so let's just see what information we have here. So we're following with the same circle. They touch internally at the point B, as we can see there. We have the radius and we have the center of circle S, which is the bigger of the two circles here. So this is 1 minus 6. And I know that overall this distance, if I mark it in red, the distance out to the edge here from my bigger circle, we've already established is 6 root 10. So if I was looking at internally, that would be D there. Okay, I also know the coordinates of B, which are 7, 12. Okay, I know the coordinates of B here. So we, I suppose, again, have two different ways that we can look at this one. We have two different ways that we can kind of approach this one here. The radius of C is 1/3 the radius of S. So the radius of C is 1/3 6 root 10, which is going to be 2 root 10. Okay, so that's, I suppose, this one in here. So we have 2 root 10 in here. So comparing those two, okay, or comparing where that leaves me with then, this distance from here to here then will be 4 root 10. Okay, so 6 root 10 take away my 2 root 10 gives me 4 root 10. And I know they touch internally. I know that that does hold. So I know that's kind of what I'm looking at here. Okay, so trying to fill out everything here. So I have my circle, my center S. Let's just use S, I suppose, for that point that is the center of circle S. We'll then come to that point K, which is center of circle C, and then we come to my point B then on the outside here. So I have the point 7, 12, the point K is unknown, and this point is 1 minus 6. Looking first of all, I suppose, at the overall distance that I'm going here, this is going to be plus 6, and then plus 18. And I know that what's happening here is actually a distance between these two of 4 root 10, and then between these two of 2 root 10. Okay, which is going to be a 2:1 ratio here between my points S and B there, being split in a 2:1 ratio by my point K. Okay, so I can use my divisor of a line segment here, or I can use my kind of movement idea either. Either will work. If we go divisor of a line segment, I'm looking for the point that will divide this line segment into a ratio of 2:1, using these points that I have here, 1 plus 2, 1 by minus 6 plus 2 by 12 over 1 plus 2. So I get 1 plus 14 over 3 minus 6 plus 24 over 3, and that's going to give me 5 and 6. Okay, the point 5, 6. If we want to look at it in terms of movement, then I need to move 2/3 of the way. So given that I know it's a distance of plus 6, 2/3 of that will be going a distance of 4. Don't know why I'm multiplying it out. 4. And 2/3 of the other distance of 18 will be 12. So I need to go plus 4 plus 12. So 1 minus 6 plus 4 plus 12 is going to be 5, 6. Okay, so kind of easy to show, or good to show here, that comparison between divisor formula and translation idea. Whereas then to find the equation of C, well, we know that the center of C is K, which we've established is 5, 6. The radius is 2 root 10. So I can use my formula here, x minus 5 squared plus y minus 6 squared equals 2 root 10 all squared. So x minus 5 all squared plus y minus 6 all squared equals 40 as my equation of the circle there. Okay, so lots of different things going on throughout these questions here, and a lot of different things that they're testing really throughout. Trying to show here, I suppose, some different ways that you can approach these questions. Some of them there probably could be done a bit more methodically. You could do with your intersection and all of that idea. I think it's good to show that divide with the line segment, because sometimes that will present you with a much easier way of doing the questions as opposed to finding those points of intersection, particularly if you're tight for time doing some of these questions here. But you can see overall that generally there's multiple ways of doing it that all take you to the same place. So it's about going with the one that you're most comfortable with, really,